Good evening. My name is Henk Broer, and I am the chairman of the Johann Bernoulli Stichting for the Wiskunde. It's my honor and pleasure to welcome you all here and in the live stream to the 2024 Johann Bernoulli Lecture. Johann Bernoulli Lecture is an annual event initiated by the Johann Bernoulli Stichting, dedicated to Johann Bernoulli, one of the most famous, present company excluded, famous Groningen mathematicians, who worked here for 10 years around 1700. The lecture features distinguished speakers who present lectures on various topics in a wide area of mathematical sciences. This year, the 33rd lecture, our speaker is Professor Ute Ebert from the CWI and the TUE, Technische Universiteit Eindhoven, CWI, Centrum Wiskunde Informatica. I know Ute Ebert from the NWO, FOM, all abbreviations, doesn't matter. Some national thing on mathematical physics that ran around the turn of the century, last turn, and I am happy that she is with us today to talk about one of her favorite subjects, lightning. Our colleague, Professor Ton Schoot-Uiterkamp, will now introduce the speaker further. Note that after the lecture there will be a round of questions, and after that everybody is invited to drinks in the Spiegelzaal below, the ground floor. Please, Ton, the floor is yours.
It's a real pleasure to be in front of you because it's a rather unusual situation tonight. It's the 33rd Bernoulli lecture, but the first time that this lecture is being held together with the KNG, the Royal Physical Society, KNG, Koninklijk Natuurkundig Genootschap Groningen. My name is Ton Schoot-Uiterkamp. I'm the vice chairman of the KNG. And as of this year, we have decided to join forces together with the Bernoulli Foundation because it's important for the audience of the KNG to also emphasize that we are not only presenting lectures in chemistry, physics, biology, medicine, but also in mathematics and in computer sciences. And by combining forces, that seemed to be a right way to do so. I should also emphasize that we are organizing this evening together with Studium Generale Groningen. Without Studium, this hall would not have been filled. Especially the younger population would not have known about this lecture because they don't read journals or whatever. And I'm 80 years old, so I'm forgiven for what I just said. Tonight, it's a real pleasure and honor indeed to introduce to you Professor Ute Ebert. She got her physics training at the University of Heidelberg in Germany, and then she did her PhD in physics at Essen-Duisburg University before she went on to go to the Netherlands in 1998, where she was for 4 years working in the physics department of Leiden University before going to the CWI, that was already referred to by Henk, the Center for Mathematics and Computer Science. She's been the head of the group of Multiscale Dynamics since 2002, and since that time she has also been professor at the university, the Technical University, I should say, of Eindhoven. Professor Ebert has had the distinguished role of PhD students, and she is also very well known for her outreach activities, and that has to do with the topic after all, most of us have heard or been through a thunderstorm, and the topic of lightning, of course, is something that sooner or later comes and crosses our path during our lifetime. And not only during our lifetime, it's also a topic that is as old as mankind. Jupiter, Zeus, Donor, Thor, all gods of thunder and lightning. And so it's a topic that is really very well deeply ingrained in mankind. But it's only in the last decades or so that we have begun to understand what the phenomenon of lightning is all about. And the person who is best of all equipped to tell us more about this is the person I'm going to introduce right now, Professor Ute Ebert. The floor is yours.
Thank you for the flowers, ladies and gentlemen. I already want to apologize that the projection will not be perfect. Had to switch from Mac to Windows computer, and I will probably need some assistance for the movies. You think you know what is lightning? You look at this picture already, you get zoom into the temporal evolution. But I will convince you that most of the lightning activity is actually not in this cloud-to-ground stroke. But before I do this, I just want to introduce you briefly. What I'm going to tell you about is not only my work, but there were many national and international colleagues, PhD students, postdocs, discussion. I have a list here, they're not representative. There are also various funding sources from NWO, SDW, Marie Curie Network, EU Cost, and so forth. But together they enabled me to give you an overview with my personal perspective on the lightning physics. And so what I'm going to tell you is first, give you an overview of a phenomena. First, the familiar lightning from cloud to ground, then discharges above clouds, looking down from space and looking with radio antennas. Then I will tell you about the mechanisms, first the cloud charging and the discharging. And then finally, I will go into methods and observations, simulations, and lab experiments. And in particular, because this is a mathematics colloquium, I will go a little bit more in detail about the simulations and model reduction. Okay, let's get started. The first thing is, where do you see lightning? The Netherlands are not the best place for that. As you see, this is a map that shows you the global lightning density. And you see it's mostly over the continents, and there are something like the 3 most important chimneys. If you look from left to right, you see the Americas, then south of the Sahara in Africa, and then what's called the maritime continent, Indonesia, Northern Australia, and these areas. And you see a logarithmic scale and color on the frequency of the strikes from 0.001 strokes per square kilometer per year, up to 10 strokes. So this is many orders of magnitude. On average, you've got something like 100 strokes per second worldwide. Most strikes are actually in the afternoon, in the local afternoon of one of the 3 chimneys, which actually also gives you something like a periodic modulation of the potential difference between the ground and the ionosphere. So what you see is mainly in the tropical regions where you have the thunderstorms and overland. Now, this is a recent observation that actually, if you look at the most extreme lightning strikes, the distribution is completely different. And this is what you see in this picture, the so-called super balls, which again call attention for the past 5-6 years. the superbolts have an energy that is more than 1,000 times that of a normal bolt energy. And strangely enough, they're just oppositely, so every 100,000 bolt is a superbolt. And strangely enough, they don't appear during summer, humid areas over land, but mostly during winter and over sea. And also, there are the three most important areas indicated with the color rectangles. And this is actually the northeast Atlantic Ocean. This is around in our area, but more over sea than over land, over the Mediterranean and down in the Andes. This is one of the many questions. There are first suggestions about cloud altitude, the distance that the cloud-to-ground strike has to pass, but is a recent observation that is waiting for explanation. And as many other phenomena in lightning, they're waiting for explanations. Familiar to us, as I said earlier, is the cloud-to-ground lightning, and something that we also see recently with high many frames per second video recording is how actually a lightning attaches to building. And I'm just playing this movie now. You see the lightning leader coming from above, and at the same time there are counter leaders coming upwards from the buildings, and some of them make it, others do not make it. And so this is an attachment process that, as it was previously known from, let me say, television towers or so, it was not so well known that it also happens from buildings. I will play the movie once again, and you see the different frames, the stepping of the film, and these are actually 40,000 frames per second, so nothing you would see with your normal eye, but I will play, yeah, here it comes again. So there are starters also from the building on the right, but of course in the middle, various attempts. But then two of them make it, and then everything is much too bright, and then it passes by. So what you saw here is these two stages. On the left-hand side, you see the lightning leader. The lightning leader is propagating, and on the right-hand side, you see the return stroke. That is after the conducting channel has been established between cloud and ground, when the large current and heating is going on. And we know the return stroke is extremely hot. Spectroscopic measurements tell you that it's about 30,000 Kelvin. Is this hot? Well, if you measure it in Kelvin, it is. But if you measure it actually in electron volt, it is not so much. So electron volt is elementary charge times volt. This is the typical energy scale that you have within atoms or molecules about the binding energy of electrons. And so these 30,000 Kelvin correspond to 3 electron volt. It means, okay, in this heat, molecules are breaking up and you're forming a plasma, but this is a thermal plasma. On the left-hand side, you have the lightning leader, and there the energies can go up to 1,000,000 times higher. But this is not an equilibrium state as for the return stroke on the right, but it is a very transient phenomenon, and it applies only to very few components of the gas. And just a reminder, so you have got molecules or atoms with a nucleus and an electron shell, and you have got as many negative electrons in the shell as you've got positive charges in the nucleus. But you also can have free electrons, and if these free electrons win a sufficient energy, they actually can kick out electrons, and they can accelerate to very high energies, even if most of the surrounding molecules stay cold. And so this is one of the very interesting things, what is precisely happening with these high energy electrons in the EV range and also the MEV range, and what kind of phenomena can they bring about. Now, I was talking about lightning between cloud and ground. Now, this gives you a scale over the altitude of the atmosphere, what you have above the clouds. The upper edge of electric discharges above clouds is where actually the ionosphere, so the conducting part of the atmosphere, starts. That is at about 90 kilometers altitude during nighttime. So what you see here is more or less a plate condenser with the ground at one potential. It is well conducting, and the ionosphere at 100 kilometers altitude, also pretty well conducting. And in between there is the non-ionized gas where you can have discharges. And what you see here is actually now in altitude. Just to remind you, at the very bottom of the picture, you see the clouds with an upper edge between 10 and 16 kilometers. And from there, you have the normal cloud-to-ground lightning downwards. You have the blue jets upwards. And you also have the red sprites, and actually starting at ionosphere, moving upwards and downwards and upwards. And but these discharges at the high altitudes can be so large because the pressure is so low. So on the very right, I'm actually indicating the pressure in millibar. And you see the pressure decreases exponentially by 5 orders of magnitude over this altitude. And that tells you that these discharges at this very thin air at high altitudes is ionizing much easier. And these enormous red sprite discharges are actually a consequence of the primary discharge between cloud and ground, which changes the electric field above and starts in a discharge in this area. And movie starts. In recent decades, we have identified a lot of additional phenomena, so I'm just showing a representative picture, in this case, of a terrestrial gamma-ray flash. I was already saying earlier that the energy of single electrons can reach the mega-electron volt region. That means that you get very energetic processes, including the emission of gamma rays, electron-positron pairs. There are also nuclear reactions that have been observed. And so this was a recent observation from the International Space Station, where you actually found these two phenomena together, the ejection of the gamma rays, which are indicated with this pink color, and the expanding ELV in the ionosphere. This is just a schematic. It's a visualization of the measurements that have been made from this particular ASIM platform on the International Space Station. And now I'm showing you what is happening between the cloud and the ionosphere. In the next movie, I want to go even higher. So here you see the atmosphere up to 100 kilometers altitude. The space station is at about 500 kilometers altitude. And from there, you can look down onto lightning. And now you have to help me, Nina, and start this movie. So this is a view down from the International Space Station. What you see at the moment is actually the red lights of the cities, but then you will also see some white lights popping up. And this is actually from thunderstorms. Of course, this movie is very much accelerated, and you see how it's playing all through the clouds, very extended. It's not a local cloud-to-ground strike, but it is some... Can you click again? Enjoy the view. And here the lightning is appearing at much too high speed, of course. Yes. Okay, and so I'm going to show you first a kind of, in the meantime, I would say historical picture. what you can actually learn about what's happening inside the cloud. So what you see here is actually one of the first radio measurements where you see how a discharge is developing within the cloud. So what you see in the middle, the big picture, is a top view, and you see the north-south and the east-west direction on the axis, the top view of the discharge. The other two pictures are side views. So one of the axes is the altitude, and the other one is the north-south or the east-west direction. The color is the time. So blue is the earliest, and red is the latest, and in between there are 2.5 seconds. And so what you see, the activity that you see is, first of all, extending over a length of 50 kilometers, if you look from top. And you see, if you look at the upper picture, for instance, it starts out with the blue on the left, and then the discharge evolves further above the surface towards green, towards yellow. In the end, it's red, and at the very end of the red, you see is moving back towards the left and going to ground. And so what you actually observe below the cloud is only this little part between the cloud and the ground, this last, I think, 4 or 5 red dots. And so there's an enormous activity all within the cloud, and recent observation even has said it can, lightning can extend in the cloud over 900 kilometers. Maybe not in this area, but in some places of the United States. And all of this activity is not visible to our eyes. You just see this illumination and you hear the rumbling. And so you get a lot of details when looking into the cloud. And here in Groningen, we're in a very interesting situation that we can now look much better. So here we have a world record in the resolution of the discharge now down to 1 meter. And there are actually 2 colleagues sitting here. There's Olaf Scholten and Brian Hare. There, yes. If you've got any questions about this technique, you can ask them later on. And this is again a movie that needs to start. So here you see an altitude of 5 kilometers, and you see how the discharge grows in the cloud, and somewhere at the one edge, somewhere at the other edge. I was just doing a stupid calculation saying the whole thing in the end is 5 kilometers large, and the time was so much. I calculated a speed of 30 kilometers per second, which is the speed of light divided by 10,000. But this is, of course, unfair because it's not continuously growing, but it grows a little bit here, it grows a little bit there. There are differences between the positive and the negative ends, but you cannot do a lot of interesting observations on this zooming in. And the technology is actually the law for superturb that you probably know from the astronomy groups here. There has a lot of radio antennas a bit south of Groningen, as you see on the right-hand side of the picture. And there are all these antennas which look pretty dull. There is just a stick in the middle, and then with 4 wires into the 4 corners. And the secret behind this is a glass fiber net below all these antennas that lead to a supercomputer. And that supercomputer is going, if it's properly programmed by Brian, it's going to tell you where precisely these current pulses were that emitting the radio emission that is then detected by all these antennas and reproduced to the picture that we saw earlier. Can you play it again? Yeah. Oop. Oop. We shouldn't be working both of us on this. Yeah. So you have the feeling it's almost space filling. And particularly if you know that ahead of these leaders that are growing, there is another structure that we'll show you later on, streamer coronas. So this gives you a very different picture on the dynamics. So that's important within lightning. Okay, this is my overview over the phenomena. And I now will go into the underlying physics and mathematics. So I will first talk about the mechanisms, the cloud charging and the discharging, and then about the methods. I should say that in cloud charging, there is not only thunder clouds, rain clouds that generate discharges, but there are also sandstorms, and there's volcanic lightning. And I will give you a rough picture of how the cloud is charging. But I should say that in my understanding, there is an open question whether you can actually transfer the mechanisms that you think you understand from the rain cloud towards a volcanic cloud or towards a sandstorm. I think there is still a lot of work to be done. But let's look into the rain clouds only. So this is a picture, a schematic picture of how a cloud looks like. The most important thing is there is an important line, which is the 0-degree line. Below you have got essentially water, and above you have got more ice particles of different shape. And the electric charging happens within the cloud when particles are colliding. And if you have only water droplets, you will not have a collision of droplets. I mean, you might have a merging of droplets, you might get splashes, but there is no charging mechanism. For charging, you need to be below 0 degrees, means above a certain altitude with these ice particles. And the ice particles are colliding, and for a not completely understood mechanism, there is a tendency that the heavier particles carry away a negative charge, and that means that the other particle has to have the equivalent positive charge. The collision of particles comes because within a thunderstorm you have got very strong convection and turbulence, which actually lets the particle collide. And the lighter particles are being carried further up by this turbulent motion, while the heavier particles are sinking down. But the negative particles are negatively charged. The heavier particles are negatively charged. It means you now get an area further below with negative charges, further up with positive charges. That only can happen because the mechanical forces are more important than the electric forces. Otherwise, you couldn't separate it. That means now you have got an electric field built up within the cloud. And then it's the most logical that the discharge is also within the cloud, which actually happens. So most of the discharges do not reach ground, but it is only within the cloud. For instance, you can have situations where shear winds are actually moving the positive charges in one direction and negative in the other direction, and then you might get discharges to ground. But yeah, and there's this extended activity all through the cloud. And yeah, and then also some discharges are drawn in, and that also for the same reason are mainly in the horizontal direction and not in the vertical direction. This is the electrification. And then you get the discharging. And in the discharging, you get many different phenomena, which I've all plotted here in this single graph. So, and this is all concerns the lightning before or without the strike. This is corona discharges, ionization of larger volumes through corona bursts, the streamer bursts. And on the upper part of the picture, I've again set you down the memory towards the transient luminous events on the left-hand side, terrestrial gamma ray flashes on the right-hand side. You also have got plenty of greenhouse gases that are produced. I will tell you in a moment how that works. And there's, of course, lightning attachment and a question how that happens and how you can prevent this. This is, for instance, an urgent question now with the wind turbines, which are getting higher and higher with recent technology and that need protection from lightning. On the lower part of this picture, I also show you a zoom into these very different structures. On the very right, you see the continuous lightning strike towards the ground, the propagating lightning leader, and then you zoom in and down into the scales of meters and centimeters that I'm also going to explain you what's happening. So an important message that I want to bring across is that the lightning phase before or without a visible strike is the one that generates a lot of interesting structures. First of all, the complex conducting structures that later can carry a return stroke if they connect between two conducting areas. There's generation of greenhouse gases, nitrogen oxides, ozone. There's also HOx has been found in edges of clouds where no visible discharges had taken place. And there are the high energy phenomena that are not frequent but occur regularly, terrestrial gamma ray flashes, also electron-positron pairs, and also some nuclear reactions have been shown. And the question is, how is this, when and where, how much? Can we fundamentally understand the structure and dynamics of this pre-strike phase? I would say not yet, but we have made some steps and we'll tell you which steps we have taken up to now. So now we're coming then to the methods, the observations from ground, air, and space, simulations and model reduction, and the lab experiments. And I already told you quite a bit about the observations. So let's look into the modeling. So the basic thing is what I showed earlier. You have got an atom or molecule with the same number of positive charges in the nucleus as negative charges of the electrons in the electron shell. And there's from somewhere I've got some free electrons and accelerate them in the electric field and they collide with air molecules. And because of the energy that I've gained from the electric field, there are various reactions possible. So the first one is ionization. So the electron comes in, so in the lower right, and two electrons are coming out, and one electron is missing. Now the atom is positively charged, and I get an extra free electron. Now, not every such collision is going to give you an ionization. You also get a lot of other type of collisions, excitation and dissociation of molecules. And that is actually the source of the greenhouse gases. So if the electron hits an oxygen molecule, you decompose it into oxygen radicals. The next step is the formation of ozone, and this is the characteristic smell that you have when you are close to some discharge experiments. And in the next step, this process is repeating, and the electrons are creating ionization avalanche if the electric field is high enough, and the electrons drift. So the electrons are much lower mass and therefore much higher mobility, and they're mainly moving while you, in first order, you can neglect the motion of the ions between the neutral molecules. One possibility is electron runaway. So it depends on the background electric field. If the electric field is low, you accelerate the electron, it bounces into a molecule, loses energy, and then is accelerated again and loses energy again, and then you get some mean velocity, which is a drift velocity. But if the electric field is too high, you can actually accelerate the electron, then it does not lose enough energy, and then accelerate it further, and that leads to the so-called electron runaway. And the question is, when would that take place? So one of the big puzzles, we know that this electron runaway can happen. We measure it regularly in different situations in the lab when a lightning leader approaches, or from satellites or the International Space Station. But the debate that is still going on is which mechanism in the discharge propagation is precisely providing a sufficiently high electric field for a sufficiently long time in order to accelerate the electrons sufficiently. So this is one of the open questions that people are trying to answer at the moment. And so if this avalanching continues long enough, eventually you're then creating conducting regions, and these conducting regions are then focusing the electric forces, and then you have the true nonlinear mechanism of the discharge propagation. And this showing you the streamer mechanism. You see here from left to right. On the left-hand side is the electric field, which is actually modified by the presence of the discharge that is propagating downwards. So you see a very high electric field ahead of the long channel, the red color, a very low electric field in the interior, as you typically would have if you've got a conducting body in an electric field. Only because the boundary of the conducting area is moving, this electric screening is not perfect, but some electric field is entering here. In the second picture, you see the electron density that is actually providing the conductivity for this channel to be electrically screened. Then you see the charge density, so there is a small surplus of positive charge right at the edge, and that is actually what is creating the electric field on the left. And the last picture is the calculated light emission, which is very fortunate, I should say, because it's really localized at the area where the impact ionization has taken place, and not along the whole channel, and that allows you a very interesting visualization technique. And so one of the problems, if you want to simulate these structures, is that you see there is a moving interface, so this curved space charge layer is moving downwards in space, and it's creating the electric field in which it is moving. So you have to be very accurate in calculating this electric field. And so what we have done is getting adaptive mesh refinement. So what you now see is on the left-hand side, the electric field. On the right-hand side is the space charge layer. And on the right-hand side, you also see a numerical mesh drawn over this thin space charge layer, and you see that this, some places it is very fine, and other places it is rather coarse, where you don't need a high accuracy. And this is actually the way how you can simulate with reasonable memory effort the further evolution of the discharge. And this was in particular the latest version of adaptive mesh refinement of my PhD student, Johann, who's now joined me on a tenured position at CWI. And so what you see is actually the crucial area of the ionization front. Below, on the lower part of the picture, you see on the left-hand side the high field enhancement, but there is essentially no electron density. And then you get this thin front where you have both electrons and electric field. In this area, you're doing all the impact ionization, you create electrons, you're exciting the molecules, and then you have got a channel behind that is continuing towards the top, where all these plasma and excited molecular species already have been generated and then processed further. And we have different, now the question is, how do you characterize them? You start on the smallest scale, and you have got different streamer modes. So this picture shows you actually the 4 time steps of a streamer discharge. The yellow is the electron density, and the lines are equipotential lines, means if the equipotential lines are very close, you get a very steep increase of the potential, meaning you high electric field, and where they're very far apart, you have a very low electric field. And what you see here is from step to step, the streamer is accelerating. The time step between the two pictures is 17.5 nanoseconds, and the velocity is 10 to the 6 meters per second. So the speed of light divided by 300. And you see the streamer is accelerating and is increasing in width. And you also have got this other type of discharges. This one is actually steady and solitary. So the time step between the pictures is almost 10 times as large. The velocity is much smaller. And what you also see is that behind the discharge, the equipotential lines are returning and there's no electron density anymore. So it's a fixed amount of charge that is propagating with a constant velocity downwards. So it is such a simple object that you can ask mathematical questions like, given a background ionization, how many solutions of this type do I find that propagates with a constant velocity? And the answer is up to translation invariance, there is precisely one. So what you have is a kind of a solitary wave. It's a self-organized non-linear structure that is propagating without change of shape downwards. It's a bit an exotic solution, but you can realize to a certain amount. And now solutions like on the right-hand side have the property that you have really lost the electrons behind, so you're not building a conducting channel, but the conductivity is lost. The electrons are attaching to oxygen molecules and are lost in that sense for the conductivity. And in order to build a conducting channel, you need an additional physical mechanism like heating or chemical changes or so to maintain the conductivity. And so if the channel heats up due to the current that is flowing, you get a so-called leader discharge. That is the one that you actually see on the earlier pictures about the propagation of a lightning leader. I already was calling them lightning leaders, so this is the leader discharge. And I just want to tell you that there is presently a lot of interest in characterizing these discharges also on a small scale, because the generation of ozone or nitrogen oxide is not only a question for climate science, but also of plasma technology. So if you want to disinfect something, then this is the standard way how you're generating ozone. It was actually found in 1850 by Werner von Siemens that this is the way how to generate ozone, have a transient discharge, and this is the way how you do it up till today, of course with various improvements. You're also generating NOx, so the Stickstoffproblem. Not so welcome in the Netherlands, but maybe as fertilizer in other parts of the world. You can use the ozone for fertilizing. So there is a lot of interesting chemistry there, which also requires further exploration. Yeah, as I said, because it's a mathematics colloquium, I also want to give you an idea about the step of model reduction. I was skipping earlier about the transition from the particle model towards a continuous model, where I showed you the propagation of streamers. But here I want to show you that you can do a kind of 1.5D approximation, where you do not resolve the whole structure of the front with a continuum approximation. But you characterize the channel interior just by the electric field on the axis. And you're representing the weakly curved charge layer. So it's weakly curved because the thickness is much smaller than the radius. You approximate this just by a line, and for the line you can take the approximation that is semi-spherical. And you have the avalanche zone ahead of this, and that allows you actually to build a simple model where you just have conductors with capacitance, where the head is growing, and you characterize it just by a few parameters. But this is work on the way that will allow you to take the step towards larger challenges. Namely, then I want to take 2 more steps of streamer theory. The first one is about branching, and then the second one is about larger scale discharges with very many streamers. And so first I want to tell you about the branching of streamers. So this is a technique that Sander Neidam has developed in Eindhoven. And what you see here is a camera image of the same discharge that with prisms and mirrors is actually projected on the same camera, but with different angle. And so you should project it on the same camera because the timing is extremely important, and if you would have 2 different cameras, you would need to synchronize them. And therefore you do it like this. And so this is a stereoscopic picture, and it's stroboscopic. And I was earlier saying, if you look at the streamer, we are very lucky that nitrogen is emitting light immediately within less than a nanosecond from the area with a high impact ionization. And that allows us now a stroboscopic imaging. So you have in front of your camera, you have an intensifier that you're actually driving with a voltage frequency. If the voltage is high, you get a picture. If the voltage is low, it is blocking. And now you turn the camera on and off, and in such manner you get this sequence of dots, and if you know the frequency, you immediately can read off what the velocity was. And that allows you actually to fully reconstruct the structure in 3D. Of course, this is again, the picture is a 3-dimensional projection of the whole thing, but we have the whole 3-dimensional structure, and the color is actually indicating the local velocity. And yeah, we recently had a really great experience that we were able to reconstruct with our simulations the distribution that you have for these branching events. And if I would show you the pictures, I mean, it would take you too long to look into the difference between the different pictures. But if you look at the pictures, yeah, you see it's just convincing. And what puzzles me is that if you do a simulation, you start out from really elementary knowledge that you have. Some people have calculated what is happening if an electron with a given energy hits a molecule, and which different reactions you could have, and what the probability of this is. And you put this into a particle model, as I was showing earlier with the avalanches, and you do the whole calculation, so you don't have any fit parameters, and you reproduce these simulations and these experiments. And for me, it's still a miracle because you know how many uncertainties you have about the cross-sections that you're using, about the statistical model you're using. And we are really happy that we get an agreement on this point. Now, I want to end. This is a discharges of few centimeters. I want to end with discussing a discharge that we had realized a few years ago at the high voltage lab at the TU Eindhoven. And this shows you now a discharge of a meter size, where at the upper part you have applied a voltage of 1 megavolt. And this is one instant of the discharge, and what you see is many, many streamers. And what you should imagine, I was previously showing the lightning leaders. The lightning leaders, ahead of the growing end, they actually have got a streamer corona, which probably looks somewhat like what you see here. And I will now show you various pictures of the evolution of this discharge. So in the upperst row, you see the upper electrode where you apply the high voltage, and you see the different stages of the evolution of the positive streamers propagating downwards. So what happened here is that for each next picture, previously we saw the stroboscopic imaging. Now we just leave every time the camera open for a longer time. So, and then of course, every time the path that you see is longer. So in the upper row, you see the propagation of the positive streamers downwards, and you see at the very right picture, number E, that there's already some activity from the lower electrode starting. And then in the second row, you see the positive streamers propagating further, and the negative ones already moving upwards and connecting. And then towards the end, you see there you have created conducting paths. This conductivity is still pretty weak. Now there is further ohmic heating from the current, and this is false colors, this yellow, but it and red, that indicates you that there is a higher temperature and higher light intensity in this area. Now, I was also talking about X-rays and gamma rays, and precisely at this point in time, there was a burst of X-rays of fast electrons of 200 keV. Applied voltage is 1 megavolt, and precisely at this stage, the 200 keV burst is coming out. And yeah, let's look at this. This is precisely this stage. There's a different color scheme, but the same discharge. And so what is happening is that this high voltage was propagating downwards with the streamers, and the other one was the counter streamers were propagating upwards. And because there is a low electric field inside the streamers, the electric field between the streamers has to become higher and higher. And eventually it's so high that locally you got a sufficiently high electric field for electron runaway and a generation of X-rays and also gamma rays. I'm happy to say that my colleague for my PhD student, Sander Neitam, has got a big ERC grant, and he will build an even nicer setup than what we have here. Here the voltage was rather rising slowly, so at the end of this discharge, it just had about reached the 1 megavolt, and in future we already have voltage rise within nanoseconds and then a long plateau at 1 megavolt, and I expect even much more energetic processes and a better understanding of the electron runaway and the high energy phenomena. Okay, that is what I wanted to tell you. I've got 2 more slides. So what have you seen now that was unseen? The first one is the pre-strike is too fast for our senses. It's complex and very extended. We have to take particular measures to see it. In-cloud lightning is the most frequent. So these cloud-to-ground strikes that you see, okay, they're not the most important part of the process. Of course, they're the most dangerous if something is hit on ground. I've told you about the lightning chemistry. Didn't elaborate much, but this is the same chemistry if you're in the same gas that is used in plasma medicine, plasma agriculture, and that is happening inside a lightning cloud. And I was talking about the high energy emissions, and our understanding grows through complementary methods. And it is a small field that is sitting between all disciplines, so there is no appropriate place where this type of investigations would be done. So, I mean, I'm at Center of Mathematics and Computer Science. Colleague Sander is at Applied Physics in Eindhoven. Others are in electrical engineering department. Some are in geophysics department. But there is not this one place where you say, okay, let me say, like solid state physics or a discipline like this that has got this, this is part of the physics department. And so, because there are not so many people working on this subject, there is a myriad of open questions, large-scale modeling, further steps of model reduction, the difference between the polarities, between different gases where you do the discharges. We saw in the LOFAR measurements that the motion is not continuous, but rather random. This end grows, this end grows. There is a step motion, nonlinear mechanisms that are not understood. The local conditions for the generation of high energy products like gamma rays is not really understood. The role of the pre-strike phase for the lightning chemistry, when I was talking about greenhouse gases, NOx, ozone, it is not clear in which stage of the lightning, the streamers, the liters, or the return stroke, most of the gases are produced. Traditional picture is it's in a return stroke, but I doubt that. I think I'm going to think about it further. And then the lightning protection during the pre-strike phase. What can you do before the lightning leader arrives to prevent the attachment of a lightning towards a particular object that you want to protect? And this is the overview of my talk again, with all the phenomena that I've tried to explain you. And now I welcome your questions.
Thank you very much, Ute, for this highly interesting talk. I will allow for a couple of questions. I look around.
Okay. It seemed that these lightning rods or balls are interacting with greenhouse gases more than other gases. Why is that?
I mean, there are all kinds of chemical reactions inside the lightning. Yeah. And I was just emphasizing the role of the greenhouse gases. I was not saying the other ones are not appearing.
Okay, yeah, clear. Thank you.
Yeah.
Okay, I see there a question. Marcello.
Hi. Thanks a lot for the nice talk. So, in the first video, we see on the right a big lightning coming down, and it was very furry. Was it because it's close by, and then we can see what you were saying at the end, this streamer?
Well, you mean the very first picture?
Yeah, the very first video.
Okay, I like this movie. It's a very nice movie, because if you look on internet, you will find many of these type of movies. The problem to evaluate for science is that you do not know how far away it is. You would want to have synchronous measurements, let's say, of the location, the radiation, local electric fields, and only then you can do science on it. So there must have been streamer coronas ahead of these lightning leaders, but I cannot tell you the differences, unfortunately.
Thanks.
No, you get. Yeah.
Thank you very much for this very nice presentation. The superbolt. The superbolt.
Yeah.
If I look at the picture and the distribution, it struck me that they were on the evenaar and bij de keerkringen. I don't know the English words for that, but hopefully someone else can explain it. Is there any reason for this peculiar distribution of these superbolts?
We would like to have that, yes.
Okay, now.
I mean, what the situation is, let me say, past 30 years, there have been optical observations. There is a worldwide lightning location network that is measuring actually in a kilohertz regime. There are about 70 stations around the Earth. And they were just looking to the data and say, okay, let's identify whether the tails in a distribution and what the property of these tails are. And this is the result, what I showed you. There is a paper from last year where they say maybe during winter time the electrification area is lower because it's winter time, so the 0 degree line is lower down, and then the distance towards the ground is shorter, and maybe therefore you get a stronger strike. If you have a plate condenser without any tips or so, the electric field is independent from the distance. But I mean, this is just a matter of speculation at the moment.
Question there.
Yeah, thank you very much. I have several questions, but my first question, please, is there also nuclear fusion in if there is gamma ray production? You might think of some solar-like process or star-like, yeah, with these enormous voltages and discharges.
I mean, nuclear, not fusion. I mean, fusion would be that you actually join two molecules. What has been observed, and even we have predicted it at the same time, was in 2017, is if you've got gamma rays with these energies above even 10 MeV, that is actually critical, if I remember correctly, for nitrogen. You can have nuclear reactions, and there actually have been measured by some team in Japan. Say some of the American colleagues are kind of doubtful about it, but it is not fusion. I mean, at some moment people were speculating maybe there is some deuterium or so in the atmosphere. The concentrations are not sufficient. But you do generate, in particular, if gamma rays go into nucleus, you can get neutrons out, and neutrons can travel pretty far. And actually, I don't remember precisely which reaction it was towards nitrogen or oxygen. That you then can measure this must have been a product of a nuclear reaction. But of course, there's no chain reaction or nothing.
Yeah, thank you very much.
Yeah.
May I?
You are in charge.
I'm in charge. I allow for one little more question from you.
Okay, just one more.
Thank you very much. Yeah, another question, please, is there any relationship between the Earth's magnetic field, which is continuously changing, and lightnings?
Not at all.
Let me
say, we recently have done some study about streamer discharges in magnetic fields, and I see a window, let me say, in the atmosphere of Jupiter, where that could play a role. But if you have got the Earth magnetic field, it actually gives you something like a rotation frequency in a given magnetic field. But the electrons are also colliding. And so if you do the estimate of what's happening in the Earth's atmosphere below the ionosphere, you will see it was only going to do a very small part of the gyration motion, then have the next collision, and therefore you will not see the effect. So it's a matter actually of the reduced magnetic field divided by air density, which gives you the mean free path. And that is too small on Earth. It could play on Jupiter, as I said.
Yeah, thank you very much.
There's a question there a little bit further down.
Now, behind there, I see always a question behind you.
Yes, no, it's okay, it's okay.
Thank you for your, what I would call an electrifying lecture.
Thank you.
Some 30 years ago, my wife and I were sitting before the open chimney, and suddenly, all of a sudden, a ball flash came out of this chimney. It ran over the floor for 3, 4, 5 meters, didn't leave any damage. Could you give an explanation rather than we had too much wine?
I must say I'm pre-biased because I always have trusted my mother and she has seen it as well. Yeah, there was there is a hobby physicist, a trained engineer, who in his retirement age was thinking about these processes, and he's actually collected really a number of events, in particular at some moment at the Mecklenburger Seenplatte. There was some lightning, and then there were all these lakes, and then in many houses in the neighborhood of these lakes, you would actually see something that was reminiscent of ball lightning. I should say there are different types of ball lightnings. I mean, some of them are a few centimeters, some are a meter. So, and he was suggesting that actually he even has a preprint on archive on this topic. He was suggesting that it was somehow related to open fire and the ionization from the fire, but I can't remember the details. I can give you the name and you can look up or maybe I should look up this archive article again.
I will allow for one last question by Artemi.
Thank you so much. So the talk was about our cradle, planet Earth. Two related questions. How does solar activity influence the lightning on the Earth? And what do we know about the lightning process on other celestial bodies in our solar system? For instance, on the Moon, due to ionization, electrization of the dust. Thank you.
Now, first of all, electrification of dust on the Moon, I think there is essentially nothing, but on Mars is a concern. There have got some kind of sandstorms or sort, which also electrify, and people have investigated. And what do you the other question? Oh yeah. I mean, the solar activity gives you the northern light, but it doesn't. I mean, and it creates the space weather that is quite has quite some interest recently. But it does. The solar activity doesn't go all the way down towards cloud altitudes at 10 kilometers or so. We also have speculated at some moment that actually extensive air showers could play a role in seeding free electrons in area with very few electrons to start discharges. But that requires much more energetic particles than solar particles, and really particles from outside our galaxy.
Okay, well, let's finish this by thanking you once more. And
Yeah.
Thank you. And you are invited all downstairs for a reception, Spiegelzaal. And see you next year.
No, this was the wrong one?
Als je je mouw eruit doet, dan gaat het makkelijker. Ja. Helemaal goed.
dat ze in dat gaan snelweg zien wat binnen gaat. Heb je dat al gezien bij weet je die 263